Hi, I'm Dave from Toronto, home of the Maple Leafs, and I'm here to talk about hockey sticks. No, not that kind. This kind. The kind you've seen in these diagrams, ones that you've probably seen in a textbook. And with this community, you probably all plotted the upper one by running a load test and drawing a line through a cloud of points. The top graph is throughput, or how much work gets done. The lower one is time taken, or how much it slows down. Both are actually hockey sticks, hyperbolas, but the lower one is obviously so. The time taken graph is also a measure of queue delay, how much time your program is sitting around waiting for a chance to run on the CPU. It's a pretty clear measure of performance, but in terms of how long it takes to get anything done. If you measure response time, you can build a little mathematical model like the one I used to draw these. And this one is easy to draw, a lot less work than doing a load test. But why should you care? Well, for that I have to tell you a story. Many years ago, in a land far, far away, meaning 1990 in Palo Alto, we were doing a week-long load test of a Big Sun server for a client. On day 2, we got a clean run at 3,000 simulated users, but not a good run. When we replayed 3,000 of their users simultaneously, it failed. We saw throughput and time taken numbers at 3,000 that were every bit as bad as you expected for 4,500. At the same time, I was posting results from TeamQuest model on the wall. That's the graph. It's more than a little bit of an eye test, but the engineers dove at it. If you look at the dark red bar labeled Oracle Apps Processes, you can see it's one example out of a collection of hockey sticks, each starting to slope up somewhere around 2,250 simulated users, and we're headed rapidly upward at 3,000. What we wanted, on the other hand, was a really flat line with little slowdown in response time. Our plan was to be no more than twice as slow at 4,500 TPS as at 1,500. That would have had us waiting in queue for about the same time as it takes to complete a transaction. That's not what we got. In the previous graph, the slowdown was 5 times worse at 3,000 user, which is exactly what we did not want to see. So, the slowdown was from sitting in a queue. The programs themselves were not actually slowing down. They were waiting in a queue for a chance to run on the CPU. Now to me, that's running slower. It was to the DBA too. He saw a hockey stick for DB writer, the red bars in the graph, second one in the legend, and he knew it shouldn't happen. A few minutes after I posted the graphs on the wall, the database administrator said, "That can't be right. That process should never slow down. Show me the CPU graph." Okay, I know what the problem is. See the second last bar in the CPU graph? That's the DB writer. It's getting less CPU at higher loads than at low ones. It's the most important part of the database, the part that writes the changes to the disk. If it can't write, everything else in the program has to stop doing. What he'd seen in the previous chart was the DB writer slowing down, and he wanted to know why. So he asked for a CPU chart. This is a detail of it. Once the system as a whole hit 100% CPU at 3,000 users, the DB writer percent CPU started going down. It shouldn't. It should keep going up, and less important programs' CPU should go down. In our case, one of the other programs, labeled middleware, kept going up and stole CPU from the DB writer, the opposite of what should happen. So we gave the DB writer a guaranteed minimum amount of CPU, and the system didn't slow down until the load was much higher. After some additional work, the system only started to slow down around 4,500 users, just as we hoped. So that's why I care about models. That model showed us when we were going to be bottlenecked. You can't not bottleneck, but this was way too early. The model told the DBA what was wrong and allowed us to repair it. Oh, and also saved us several days running benchmarks when we could have been working on fixes. Okay, that's why I care, but why does it slow down? Well, because I get 2 requests when I only have 1 CPU. One is going to run, and the other one waits in queue. If I get a whole bunch of requests, it's even worse. To illustrate it, let's start with a graph of green boxes, each representing 1/10 of a second. The x-axis is 1 second of clock time, while the y-axis is queuing delay. This is from an article of mine in the ACMQ, references in the last slide. The first box is a request that comes in by itself. It takes 1/10 of a second and would delay the next step by exactly 1/10, except there isn't a next step, not until later, so it doesn't delay anything. At 3/10 of a second wall clock time, the second request arrives. It is not delayed. The third one, though, comes in before the second one is done, so it has to wait before it can start, 4/10. The light gray box represents the wait time, and the fact that there's an overlap causes the total delay, the y-axis, to be 2/10 of a second. This repeats with the fourth request, which pushes the delay up to 3/10. Again with the fifth, it increases the delay to 4/10 of a second. Happily, there's no sixth, so the delay falls back to 0. You'll notice the green boxes make a slanting line at roughly 45 degrees. That's the handle of the hockey stick curve, and it's intimately related to the service time of each request. You have fewer requests on average. They tend to describe a line across the bottom of the diagram with a delay of about 1/10. That's the blade of the stick. If you have more, they'll back up just like these, creating a handle. That's what lies below the lower graph of the two we saw earlier. The yellow horizontal line is the initial response time of 1/10 of a second. The slanting one is the delay when more requests come in than the system can handle. They cross at 10 requests a second. After 10/10, it's guaranteed that some requests will have to wait. The curve between the line comes from probability. As requests come in faster and faster, the probability of them interfering with each other increases. This averages out to describe a gentle curve between the two lines. That's the slowdown we were seeing in the benchmark diagram, where the database request delay curve turned upwards at around 3,000 users in the initial experiment, and not till 4,500 after we'd fixed the bug. So that's good. The physics of queues are relatively simple. Building the mathematical models is significantly harder. Some good references are in the last slide. Fortunately, programming has already been done by real mathematicians, so I don't have to. So, you now know everything about how queues work. But why do people study them? Well, they use them for capacity planning, diagnosis, development, and repair. We'll start with capacity planning, which is where the study of queuing networks came from. In the days of mainframes, upgrades were painfully expensive, and the shortest budget was 3 years. If you overbought, the accountants would be angry at you. If you underbought, your boss would be angry at you. Good multi-year capacity plans were important. This motivated some very serious studies of the behavior of queues. You would need an extra resources by the end of the budget period. It's the same today. If you overbuy, you're taking money that should be spent on some other part of the business. If you underbuy, it's worse. In the middle of a budgetary period, when money's already been allocated and spent, you're coming back to the management with the message that they either have to short some other initiative or turn away business. You don't have the resources to take it. The same problem the mainframers had, whether you're running your own machine or using the cloud. However, if you build a model, then before each business peak, you can add just enough computing power to weather it. For this, you'll need your VP's help, as the estimates of business growth for next year, the dotted line, are a trade secret. You'll need someone to credibly promise it won't leak out. In this case, we were given a transaction count with a multiplier that we didn't actually know, but we knew the amount of CPU used at that time, so that was fine. We needed 1% in 2024, and we'd need about 4% more in 2025. It's also used for diagnosis. We had a customer who'd bought a new machine with a network accelerator, but its network performance was far worse than the machine it replaced. We measured the response time of both, and sure enough, the new machine took far longer to process the same request. A scattergram showed us the new machine always took the same amount of time to make a connection. The old machine usually took almost no time to connect, but the first connection out of each set took far longer. The rest were almost instantaneous. At this point, we saw part of what was happening. The crypto accelerator made initial connections far faster, but for some reason, it treated every single connection as an initial connection. This did bad things to throughput and response time. It turned out the old machine was run using HTTP 1.1, which uses connections. The new one, for unknown reasons, was using HTTP 1.0, which makes a new connection each time. When we fixed that, the new machine was faster on initial connections and as fast as the old on persistent connections. Diagnosis, also known as bottleneck hunting, is the general case of the crypto bug hunt. We measure individual processes, Services are microservices and the like, and look for a pattern that looks like this one, 2 increasing slowdown curves. Here we have 2 smaller services that make up a larger whole. They run in parallel, so at 7,000 TPS, process 1 is taking 4 seconds. If your target is 3 seconds, that's bad. Process 2 is much faster. It only takes 2 seconds at 7,000 TPS. So let's consider what happens if we greatly speed up process 1. Instead of process 1 bottlenecking, we move the bottleneck to process 2. It'll reach 3 seconds at some point a little above 9,500 TPS. This is wonderful. We've increased the performance by more than half. In this case, the curves were far apart. Therefore, it's worth spending time on process 1 to improve our performance. Mind you, that's not trivial. To get more than a percentage improvement, you're probably going to have to find a new algorithm that's much better than what you have. You're not going to get that from tuning. On the other hand, if the curves were close together, then improving process 1 would be a waste of time, because process 2 is as slow as process 1. There's some typical development uses of queues. Predicting how much headroom you have, that's a classic. Giving yourself a time budget for service times. Resource controls can be set scientifically. If you know your slowdown rate, you can calculate how much work you can accept. But the most direct is rejecting excess work. The root cause of capacity problems is an excess of cats for a limited supply of cat food. So, reject requests with a try later. If you've got customers who will drown you in HTTP requests, you can tell them, not now, try again later. It's a 400 code, so it means problem is at the sender end, and the sender is expected to try again, usually after they fix something. In this case, it's just that they're asking for too much. Sender programs will see the 400 do one of 2 things: stop and ask the human what to do next, or in some cases, retry when they think they'll get through. This is communicated to them by a message like this. The retry after 3600 says, retry after an hour. That you're doing that far too often is the explanation to the senders, sysadmin, that something is wrong. The good thing is they have to retry and delay however long that takes. Now, if you can take a retry after 1 or 2 seconds, then just forcing it to retry might be fine. Retry after 1. That's load limiting. But the best way of load limiting is to control how much demand the senders can send you. The classic example is TCP/IP, which returns a stream of acknowledgments to the sender. If that stream stops, the sender has to stop, cut their send rate, and only then start increasing it again. Doing that creates a sawtooth graph like this. Every time the sender starts getting too fast, they get slowed down. If the network gets busier, you get a drop at lower throughput and slow down proportionally. If the network gets faster, the drop is at a higher speed, and the sender slows down less. This is lovely. The sender gets a fair share of the bandwidth and adjusts their speed to the highest the network can handle. Of course, that doesn't mean that people won't try to cheat on TCP by asking for more priority or buffering up masses of data to take all the bandwidth the channel has. And they'll make mistakes, in part by adding buffers, but more often by not updating hardware, and especially by not using the most modern software, the cake queuing discipline. Sure enough, if you cheat on the control mechanisms, you get queues as soon as you exceed the bandwidth delay product, as explained in this article from Jim Geddes and Kathleen Nichols. You may recognize the curves they illustrate here. What do you do about it? You defend the control demand. People will try to cheat the algorithm and get more bandwidth. This is the same as managing your unread books. The picture is effectively what TCP does. If clamping down on the reader's credit card doesn't work, we can always hit the router with a hammer. For an example of defending the very best algorithms, have a look at Cake and LibreQoS, where QoS stands for Quality of Service. This is a project and program for defeating terrible hardware and ancient software by slightly extending the TCP algorithm and by defeating all the ways it can go wrong or be subverted. An obvious part, but nothing like the most important part, is reducing the sawtooth. Cake and LibreQoS send slowdown headers as soon as the sender starts to get close to the limit. So any sender that wants to maximize their throughput will respond, producing this graph instead. It's not just better for the recipient, but for the sender as well, because you don't have to slow down as much. LibreQoS, as I said, is the subject of my newest ECM article. And that's it. At this point, you now know everything I've learned about queues in the last 10 years. Go fix something. Thank you. Let's connect.